Hello and welcome to lecture 18 of analog integrated circuit design. What we will do first of all today is to look at again the stability with a 2-stage feed forward op amp and ascertain how far the 0 must be from the unity loop gain frequency. Okay. So far all we have said is that it has to be within the unity loop gain frequency. We have not discussed how much, that is what we will do now. Okay. I will assume that there is a load conductance GL and CL. This is the model we have been using. GL absorbs the output conductance of these transconductors as well, and there is a GO2 here and a C2. Okay. This is the input to the op amp and this is the output of the op amp. We know that the Bode plot of A or V naught by VE is of this type. There are 2 poles and a 0 before the unity gain frequency, and the unity gain frequency itself equals GM1 by CL, because in this region of frequencies only this path is active and we have GM1 divided by SCL to be the approximate transfer function. Now, what we want to do is to evaluate the expression for the closed loop gain when this is placed in feedback. Again, we will just do the simpler case of unity feedback. If you have any other feedback, you have to substitute the unity gain frequency of the op amp by the unity loop gain frequency appropriately. Okay? I think you can do that by yourself. Also, we have a finite DC gain here. Okay? In fact, it is to increase the DC gain that we went to 2-stage op amp. But if we put all of this detail into the expressions while evaluating stability, it becomes quite complicated. Also, I have mentioned earlier that the stability depends on what happens in this region. Okay, what happens to the loop gain in that region. We know that stability criterion, which is the Nyquist criteria, talks about encirclement of -1 0, which relates to how the loop gain curve behaves around the unit circle, where it enters the unit circle from. Okay. So, we have to model this part accurately, but this part around DC is not so necessary. Okay. So, what we will do is we will act as though the DC gain is infinite, which is clearly unrealistic. As I said, it is because of finite DC gain that we go to a 2-stage structure and 3-stage structure and so on, but here we are only looking at stability. So, I will remove these conductances, which makes the gain infinite. The gain is infinite through this, also infinite through this path. Okay. In fact, the Bode plot will look something like that. This part will be the same and we will have that one. Both the poles will be at the origin. Okay. When we do not have conductances, that is what is going to happen, but this is accurate in this region. So, it is perfectly fine. Okay. So, with this simplification, the transfer function of the op amp V naught by VE can be written as, we know that V naught has a contribution from GM1 and GM3. The current in GM1 and current in GM3 get added up and pass through CL. So, the total current divided by SCL is the voltage. So, we will have SCL in the denominator and we will have GM1 plus the term representing the current coming out of GM3, which is GM2 by SC2, that is the transfer function from VE to this node, and from there to here is GM3. Okay. And this can be written in many forms. I will choose a particular form for convenience. I will write it as GM1 by SCL times 1 plus GM2 GM3 by SCL times GM2 GM3 by GM1 times SC2. Okay. Now, this is in a slightly non-standard form, but it is convenient for our analysis. So, V naught by VE is of the form the unity gain frequency of the op amp. I will just refer to it as omega u divided by S, that is what is outside, that is GM1 by CL, okay, GM1 by SCL, 1 plus C1 by S. Normally, we express things as polynomials in S, but in this case I have the opposite. Okay. This can also be written again as omega u by S, Z1 by S, 1 plus S by Z1. Okay. And this is nothing but A of S. I know that omega u is GM1 by CL and this is GM2 GM3 by GM1 times C2. Okay. Now, let us say I make a unity gain amplifier with this. Now, I will not evaluate V naught by Vi again, we have done it many times. It will simply be k by 1 plus k by A. Okay. I said a unity gain amplifier, here I am making an amplifier of gain k, okay, not unity gain. And this will be nothing but k times the reciprocal of this whole thing. This is A. So, 1 over A is S square by omega u times Z1 divided by 1 plus S by Z1, okay, which when expanded becomes k 1 plus S by Z1, 1 plus S by Z1 plus k S square by omega u Z1. Okay. Now, the DC gain is k exactly because we assume that the output conductances are not there. So, the DC gain of the op amp is infinite. Okay. There is a 0 in the closed loop transfer function and there are 2 poles. Okay. Now, how did we evaluate such a case earlier? We looked at the damping factor or we can equivalently look at the quality factor and we saw that whether the damping factor was appropriate, that is whether there would be a lot of ringing, whether the system was under damped, over damped or critically damped. Okay. We will do the same thing over here. Now, we also see that this omega u by k can be shortened to the unity loop gain frequency. This is what we have been doing earlier also, right. So, the unity loop gain frequency of the closed loop function will be the unity gain frequency divided by k if it is a first order dependence. Okay. If the loop gain has first order dependence, that is the case. That is what we have. And comparing the denominator to the standard form, which is what will we get? Omega n is square root of omega u loop times Z1 and zeta will be okay. In other words, it is half square root of omega u loop divided by Z1. Okay. So, the damping factor zeta equals half of omega u loop by Z1. If we want critical damping, we can evaluate it for whatever we want, but for critical damping zeta equals 1, which means that Z1 should be omega u loop divided by 4. This confirms our earlier intuition that the 0 must lie within the unity loop gain frequency, okay, because we have 2 poles within the unity loop gain frequency. For stability, for good behavior, we should have 0 also within the unity loop gain frequency. This tells you that for a 2-stage feed forward compensated op amp, the 0 should be 4 times below the unity loop gain frequency. Okay. In fact, if you recall the case where the op amp was an integrator with a non-dominant pole, for critical damping the non-dominant pole had to be 4 times greater than the unity loop gain frequency. Here the 0 has to be 4 times below the unity loop gain frequency. There is some symmetry in the results which also makes it easy to remember. Okay. Now, we also see that from this particular expression, if you move the 0 to lower and lower frequencies, the damping will become more and more. Okay. You will have higher and higher damping factors, and if the 0 approaches the unity loop gain frequency, if it is equal to the unity loop gain frequency, the damping factor is half, which is acceptable, but it will have a slight ringing. Okay. Anything lower than that, you will have a lot of ringing. Okay. So, now what is the value that we must really choose? Now, in case of an op amp with which was an integrator with a non-dominant pole, the non-dominant pole had to be at higher and higher frequencies, but it is actually difficult to push things to higher and higher frequencies, okay, because of constraints on power dissipation and so on, which we will see later. We will find that if you say that the non-dominant pole has to be like 100 times higher than the unity loop gain frequency, it is a difficult thing to do. In fact, the only way to do that is probably by reducing the unity loop gain frequency, okay. Whereas this constraint looks different. This says that the 0 has to be below the unity loop gain frequency. Now, is there any limit to any lower limit to the 0? Let us look at the expression for the 0. Okay. Let me also write the expression for the unity gain frequency, which is GM1 by CL, and the unity loop gain frequency of course is GM1 by CL divided by K. Okay. Now, how do we make this 0 smaller and smaller? We could reduce GM2 or GM3, or we could increase C2. Okay. Let us say we do not play around with GM1 because that also influences the unity loop gain frequency, but the other 3 things we can play around and with and independently control Z1. Okay. So, it looks like we can make it arbitrarily low, that is we can push the 0 to arbitrarily low frequencies. Okay. It turns out that is a great disadvantage. Although the stability criterion is satisfied, there will be other problems. I will not evaluate this completely analytically. What I suggest that you do, you take it as an exercise and you evaluate the step response corresponding to the transfer function that we have. Okay. Omega u loop of course is omega u by k. So, this takes some algebra, but with knowledge of Laplace transforms you can do this and also sketch it. and see what happens if the 0 moves to lower and lower frequencies. Okay, then you will get the point. I will only explain it intuitively here. Let me copy over the schematic of the feed forward compensated op amp. And what is the amplifier that I built? I took this feed forward compensated op amp and placed this in a negative feedback loop. Okay. So, what do I mean when I say the 0 is realized at a very low frequency? The 0 is pushed to a very low frequency. Either GM2 is very small or GM3 is very small or C2 is very large. Okay. In each of these cases, you will see that either the voltage here is very small or finally, the current output from this is very small, rather it builds up very slowly. Okay. If you have a given voltage here, if C2 is very large, it has to charge up slowly and that will charge up very slowly and this current builds up very slowly. Okay. The current magnitude is very small in the Laplace domain, but if you have a step input between these two, between the inputs of the op amp, the current here builds up very slowly, that is what it means. Okay. So, that is the meaning of having a very low frequency 0. Now, what is the effect of that? So, that means that let us say I apply a step input to this one. Okay. Now, initially the output voltage is at some value and it will not change instantaneously because it is across a capacitor. So, the voltage here, the feedback voltage will not change instantaneously. Okay. This is a phenomenon we have examined earlier. Even with an integrator, if you apply a step to the input, the output does not change instantaneously, but it starts ramping up. Also, now we are saying that, so effectively that means between the inputs of the op amp you have a step input because this has not changed. Okay. We also said that the current that is coming out of GM3 is very small, it builds up very slowly. So, initially it is very small. So, initially it is like having only the single stage op amp GM1 and CL. Okay. So, this is all we have. Let us imagine that this GM2 is very small and GM3 is very small and C2 is very large, that is the 0 is at a really low frequency. So, that this current does not build up much, right, in the beginning time period. So, what happens? If I apply a unit step, the output is supposed to build up to k times the unit step. So, let us say this is 1 and this is k. Now, since the current here is very small, we practically have a single stage op amp in our circuit. So, it builds up to something, and also we know that the single stage op amp has a very low DC gain, that is because of any resistors loading it, and it is also because of its own internal resistances, okay, which I did not put earlier, but this has to be included here. So, it builds up to some value which is basically k by 1 plus k by A naught prime. Here A naught prime refers to the DC gain only of this path, okay, GM1 and GO1 and the resistances and so on, which is very low. That is why we put the other two stages in the first place. Okay. Now, after a long time, the current output of the transconductance GM3 starts to build up significantly. So, what happens is after that, after a long time, this builds up and comes closer. Okay. So, although the DC gain of the op amp is high, it takes a long time to reach the low steady state error implied by the high DC gain. In fact, the reason we want high DC gain is so that the steady state error is very small, but if you push the 0 to very low frequencies, what happens is initially it builds up to a large error which is governed by the DC gain of the single stage op amp found by GM1, and after a long time you achieve a low steady state error, which is given by the high DC gain of this path. Okay. So, it is not beneficial to push the 0 to very low frequencies. In fact, it is harmful. It defeats the purpose of having a 2 stage feed forward compensated op amp. The reason to go to 2 stages was to provide high DC gain, but you have to wait forever to reach that. So, while the 0 has to be lower than the unity loop gain frequency, you can't go crazy and push it very low. Okay. Now, you please analyze this using Laplace transforms, and the conclusion that you draw must be consistent with what I have shown here. You have to plot it for many different cases of 0 to be able to see this. Okay. Now, because of this reason, right, because the output builds up and then builds up slowly, this kind of feed forward compensated op amp is not necessarily suitable when you have step like inputs. It is when you have step like input, the input appears rapidly, this single stage responds, and these 2 stages respond much later. Okay. So, for step inputs this may not be the best choice, but for other kinds of input where you do not expect a step, the feed forward compensated op amp can give you pretty good performance. Okay. Now, another exercise which is just to evaluate the effect of the 0. We have our closed loop gain V naught by V I to be k times 1 plus S by Z 1, 1 plus S by Z 1 square by omega u loop times Z 1. Okay. So, this is what we have. Please plot the magnitude of V naught by V I versus frequency again for different values of Z 1. Okay. You take let us say Z 1 to be omega u loop by 4, that corresponds to critical damping, you do that, and in particular contrast this with what we had earlier when we have an integrator and a single non-dominant pole. I believe the expression was something like this. Where omega u loop is the unity loop gain frequency and P2 is the non-dominant pole. The important difference between these two is the absence of the 0. Okay. So, you do this for different values of Z1 here and different values of P2 here, okay, and you can compare the two cases when the damping factor is the same. Okay. For instance, for zeta equals 1, we have Z1 to be omega u loop by 4, or in the second case P2 to be 4 times omega u loop. Okay. For the same damping factor, you can compare the transfer function magnitude of V naught by V I over a range of frequencies and then see how they compare to each other. That also gives you another point of choice. Okay. When you have more than one solution, you have to compare different performance metrics and see which one to choose. It will kind of become obvious why one might be more advantageous compared to the other one. Okay. So far we have discussed feed forward compensated op amps, which is an alternative way of getting high gains to Miller compensated op amps. Now, you can make feed forward compensated op amp stable. You have to make sure that the number of poles minus number of zeros before the unity gain frequency is 1. Okay. At the unity gain frequency, you have only GM1, the main op amp that you started with, that is active. All the other stuff is active before that and goes away. Okay. That is the bottom line as far as stability is concerned. Let us say you have a feed forward compensated op amp which you have designed for an amplifier of gain 1, and then you use the same feed forward compensated op amp in an amplifier of gain more than 1, you may find that it is unstable. This will not happen with Miller compensated op amps. Okay. So, feed forward compensated op amps have to be designed for each value of gain specifically. Okay. And another issue can be that if the zeros in the feed forward compensated op amps are much lower frequency compared to the unity loop gain frequency, you will have very slow settling. Okay. Effectively what happens is you have only the single stage acting initially and the other stages which have multiple stages in cascade kicking only much later. So, that means that the low steady state you are hoping to get by getting a high DC gain will appear only after a long time. Okay. That limits the speed at which you can operate the op amp, and that can be a limitation as well. So, that tells you that the zeros cannot be pushed to very low frequencies compared to the unity loop gain frequency. Okay. So far we have macro models of op amps, that is design of op amps at the transconductor level. We have not yet decided how to make the transconductors using transistors, that will come in later lectures. We know how to make op amps, we know how to enhance their DC gain, we know the main limitations. What we will look at next is some macro level characteristics, block level characteristics of the op amp that you will see in the data sheet, and we can guess at what these characteristics are just by knowing something about circuits, what limitations they bring in. Okay. So, that when you look at an op amp data sheet, you will understand why you will understand what those different terms are. Okay. So, I will first start with a single stage op amp. The most op amps that you buy off the shelf and use it in the lab are not single stage. And most of them turn out to be a two stage Miller compensated op amp. This is the two stage Miller compensated op amp. Okay. In fact, most of the commercial op amps that are available are this variety, but they invariably include a buffer. This is because you could use it with very heavy loads. They use a buffer so that the behavior of the op amp is not affected significantly by the load. Okay. So, this is the most popular variety. Now, what do you see in an op amp data sheet? What is it that we want from an op amp? First of all, we want a very high DC gain. So, the DC gain is usually given, even the DC transfer characteristic is given, DC V naught versus Vi. Okay. We want a high DC gain. So, that means that we must have a characteristic with a high slope. Now, what happens is that the op amp is operated from some supplies V plus and V minus. Okay. There is an upper supply and a lower supply, which could be anything. And this is a plot of V naught versus VE. Okay. V naught versus VE. Now, if you operate from some supply rails, it turns out that the op amp's output voltage cannot go beyond the supply rails. Okay. So, let us say the V plus is there and V minus is there. It cannot go above V plus or go below V minus. In fact, it cannot even reach V plus, usually it stops somewhere below V plus and somewhere above V minus. Okay. These are known as the saturation voltages. I will call it V sat P and V sat M, the positive and negative saturation voltages. They may or may not be equal to each other. Okay. That is the gap between V sat M and V minus, the gap between V sat P and V plus may or may not be equal to each other. Okay. And you have to determine what V sat P and V sat M are from the data sheet. Now, when that information is not available, it is a reasonable approximation to assume that V sat P equals V plus, that is the upper supply voltage, and V sat M equals V minus. Okay. These things you may be knowing from your basic electronics course, but I am just reiterating that. This is part of the data sheet. Basically, this plot tells you the DC gain, but also the limit of voltages over which you get a high DC gain. Okay. We will later see when we make the op amp with transistors exactly what these limits are compared to the supplies that we use. Okay. The important thing also is that it is related to the supplies that you use. Now, this V minus and V plus could be some positive and negative voltages with respect to ground, or V minus could be 0 and V plus is a positive voltage and so on. These limits are correspondingly relative to V plus and V minus that you use. Okay. It is not that V sat P is plus some voltage and V sat M is minus some voltage regardless of the supply. So, that is one limitation. There is a limitation on swing limit, those are the saturation voltages. Okay. Now, in addition to this, it turns out that this can be understood by looking at the single stage op amp itself. It is not only the voltage output of a circuit that is limited. If you realize a transconductor, the current output from that also will be limited. Okay. This just has to do with the design of the transconductors. It will be limited to some high value or low value, but it will always be limited to some value. Okay. What does it mean? Again, we can remove this output resistance of the transconductor and analyze it. If the current from this is limited, what it means is, as you go on increasing the input voltage to the op amp, okay, the output current will go on increasing, but at some point it will stop increasing and it will become a constant. Okay. I will simply use GM1 and C and VE, and I look at VO versus T. Okay. And I assume that V is a step of various size, right. So, maybe I will apply a small step, the output voltage will ramp up. I will apply a larger step to the input, the output voltage will ramp up faster. But what happens is, beyond a certain value of the input step VE, okay, the current here does not increase anymore. So, let us say the current is I max, and the slope of the output, which should have been, what should it be? It should be omega u times VE. Okay. Now, when the current reaches its maximum value, the output voltage will have a slope of I max divided by C, and it does not depend on VE anymore. Okay. Before that, it would have been GM1 times VE divided by C, but GM1 times VE, this relationship is obeyed only when the output current is below I max. So, it is I max by C. Okay. So, what it means is, it is not linear anymore, the output slope does not increase with the input step, and this limitation is known as the slew rate limitation. Okay. The slew rate is given by I max by C, and usually there is a slew rate in the positive direction and a slew rate in the negative direction, which can be different from each other. Okay. And both these will be specified, and this is nothing but the maximum rate of change of output voltage VO, and SR plus is when VO is increasing and SR minus is when VO is decreasing. Okay. Now, when does this come into picture? When you have cases where the output voltage has to change rapidly, this typically happens when you have high frequency voltages of large amplitudes. The output will be limited by slew rate. Okay. The output amplitude still may be smaller than the saturation voltages, but the op amp will still behave non-linearly. Okay. And it can also happen when you apply an input step to an op amp amplifier. Let us say the op amp has a unity gain frequency omega u, and I apply Vi, which is a step, of some size, and that is V O. What do I expect if I apply an input step of delta V? Okay, this is V I. The output must reach k times delta V. What it does is, initially it starts off with a slope of omega u times delta V, okay, and then asymptotically reaches k times delta V. This we have seen earlier in our original analysis of the negative feedback amplifier. Okay. Now, what happens is, as you go on increasing the input step, there comes a point where omega u times delta V exceeds the slew rate of the op amp. So, at that point, even if you increase the size of the input step, it always starts at a slope equal to the slew rate, and at some point it reduces and it asymptotically reaches k times delta V. Okay. So, this means that basically the output will not be linear with the input anymore. Okay. So, that is something to be kept in mind. So, these things become important when you are looking at the amount of settling error after a given time. Okay. So, let us say after a given period t naught, you are looking at how far the output is away from the desired value of k delta V. Okay. Now, if you assume a linear model, if the op amp is an integrator, this value is some constant fraction of the input. Okay. It is related to omega u and the amount of time that you have. Now, because of slew rate, this fraction will not be constant, it will be non-linearly related to the input. Okay. But this also can lead to non-linearities in some circuits. So, that is why when using an op amp or when designing an op amp, you have to be aware of the slew rate. Now, in addition to this, we know how the op amp works. It compares the input and the feedback quantity, takes the difference and integrates the difference. Now, any error in taking the difference means that there will be an error finally, okay, because the input to the integrator must be 0, and we assume that the input to the integrator is exactly this minus that one. Okay. If it is not that, right, if the integrated quantity is not V I minus V naught by k, okay, in general the input to the op amp is V E and the output should be omega u integral of V E dt. Now, in general it turns out this is not the case. You will have V E plus some other errors. One of them is known as V offset, it is a constant with time, and there is also a V n, which is a noise which is varying with time. Now, these are random quantities. If you measure V off and V n for a large number of op amps, you will find different values for each of them. Okay. V off is a constant with time, but it is different for each op amp. V n is randomly varying with time, as well as it is different for each op amp. Okay. So, these things will cause an error. So, that means that the accuracy to which the feedback quantity tracks the input quantity is limited by these numbers. So, V off and V n are also given in the data sheet, and the output will have some contribution from V off and some contribution from V n. Okay. And finally, we also have the magnitude response and possibly the phase response as well. The op amp, and these are evaluated with small signals, and this is basically the Bode plot of the op amp, so that you can ascertain stability. So, you will be given magnitude of A and angle of A, and most of the commercial op amps will have this Miller compensated structure, the dominant pole compensated structure, meaning there will be a single low frequency dominant pole below the unity gain frequency of the op amp, and all the non-dominant poles and zeros appear beyond omega u. Okay. something like this. The angle of A also will be given, and from this you can figure out the phase margin. This will be the phase margin if the op amp is placed in unity gain. Otherwise, you have to go to the appropriate gain curve. Omega u by k will be the unity loop gain frequency, and you have to look at the phase at that point and ascertain the phase margin of such an amplifier. Okay. So, that will be in the op amp data sheet. So, when you look at an op amp data sheet, you can expect the DC gain, DC V naught versus VE. In our notation, VE is the input to the op amp, V naught is the output, and this will also include saturation voltages. Okay. And these are functions of the supply voltages that you use. It will have the AC magnitude response, which basically means the magnitude of the op amp gain and the phase of the op amp's gain. Okay. It will mention the slew rate, and it will also give you the offset and noise voltages. Exactly how the offset and noise voltages are specified, we will see later. Okay. Now, in addition to these things, there may be a number of other limits mentioned, that is maximum supply voltage and maximum load current that it can supply, and so on. So, next time you take an op amp data sheet, please look for all of these things and try to understand where they come from. Now, I said that we will have these limitations by looking at what happens in a single stage op amp, but exactly the same thing happens in multi-stage op amps as well. So, these specifications are general. Exactly how they relate to the topology, we will see when we come to transistor level op amp design. Okay. And also the other thing I said was most of the op amps are dominant pole compensated op amps. Okay. So, again this term frequency compensation is a term that says that the op amp is made to behave like an integrator around the unity loop gain frequency. Okay. That is what ensures stability. You hear things like frequency compensation is used to ensure stability. What it means is that the op amp's characteristics are such that around the unity gain frequency you have 20 dB per decade slope or first order behavior or behavior like an integrator. Okay. That process of getting that is frequency compensation. In our case, we started with the integrator as the model for the op amp. So, we did not use this term as often as you may find in other books. Now, finally, one more thing about standard op amps that you see. Most of them are unity gain compensated. Which means that if the op amp is connected in unity negative feedback, it will be stable. Okay. That is, if you make an amplifier like this, it will be stable. I also said that they are dominant pole compensated op amps. So, the magnitude and phase do something of this sort. Okay. The non-dominant poles and zeros occur beyond omega u, and you have the angle going off like that. Now, because it is dominant pole compensated, if you make an amplifier with any other gain k, the stability is guaranteed. This we saw earlier. Okay. For a larger value of k, this will be omega u loop. Okay. Now, the stability is guaranteed, but there is a disadvantage, there is a price that we pay by compensating it for unity gain, that is that omega u loop is smaller than omega u. If k is 10, omega u loop is 10 times smaller than omega u. Now, what is omega u loop? It is basically the range of frequencies over which you have significant loop gain. Early on in this course, we saw that the negative feedback amplifier behaves more or less ideally up to a frequency of omega u loop, because the loop gain is significant up to that frequency. When you make an amplifier with this, the closed loop bandwidth will be omega u loop. Now, let us say you intend to make amplifiers only of gain 10 or more, and you use a unity gain compensated op amp, okay, which has a certain omega u. That means that you can get a bandwidth of only omega u by 10 or lower than that, okay, and that is a great disadvantage. Now, this unity gain compensation is not necessary, because you never intend to use the same op amp in unity gain mode anyhow. So, there are also op amps which are not unity gain compensated, which are available. Okay. So, usually these are compensated for k greater than some value. An example of this, I think you can see from the data sheet, is OPA 657. Okay. Now, what does it mean to have an op amp that is not compensated for unity gain? Let us say it is compensated only for gains k greater than 10. So, that means that the Bode magnitude plot and the phase plot look something like this. You will have the dominant pole here, and if you measure only the op amp, the non-dominant poles occur before the gain of the op amp reaches unity, but you will never put this in unity feedback. Let us say you put it in a feedback loop of gain some 10 or so. So, then what happens is, you have something like that, where unity loop gain now falls below the non-dominant poles. The phase of course will be the same for both. This will be the loop gain for unity feedback, okay, and it will be unstable, whereas this will be the gain for let us say k greater than 10, and it will be stable, okay, for k equals 10 let us say, and for any value of k greater than 10 it will also be stable. Now, this kind of compensation is used, that is the op amp not being compensated for unity gain is advantageous when you want to realize high gains and also realize high bandwidths, because the unity loop gain frequency limits the bandwidth of your circuit. There is no point in artificially limiting the unity loop gain frequency by compensating it more than necessary. Okay. So, if you look at the data sheet of this particular op amp, I think it says that it is compensated for gains greater than 25, and it also shows you the response of the op amp when you make an amplifier of gain equals to 25 and so on. Okay. Now, by comparing the Bode plot of this with some other op amp that is unity gain compensated, you will be able to understand all these things. So, thank you. I will see you in the next lecture.